Thanks. Thanks for having us here. We have a couple of people from Stamen at the conference. NACIS is the nicest. I've been really enjoying it. You've all been very welcoming. Thank you. So I'm the founder of Stamen Design, mostly based in San Francisco. And in the pandemic, we developed a meeting called Show and Tell, where every Friday in the morning we get together and, yeah, there's Ross. We get together and we show what we're working on. And really the point of all of this is to inculcate into us a sense of showing work in progress. So we're not just showing work that's already done, but we're showing work that's being done. And there's the amazing Ross Thorne's contribution of these Dungeons and Dragons maps that he's been making. If it's relevant to Stamen, it's fair game in the meeting. And I, at one of these meetings, showed some of these drawings, which I know you can't see, but I just wanted to show you them, that this is the form of it. And I've been investigating a couple different things, including making my own ink, but also investigating the golden ratio. Charlie Lloyd piped up and said, I use the golden ratio in my cartography work all the time. So my ears pricked up, and the two of us together developed this presentation and had a conversation about the golden ratio and what it can be used for in cartography. Now, can I just get a show of hands? Does anybody here know what the golden ratio is or how it works or anything like that? Oh, quite a few. Okay, that's great. Well, does anybody use it in their cartographic work? Couple. Okay, cool. So this will be fun. So what is the golden ratio? Okay, so there's a lot of talk about it. There's a lot of talk about how it's behind the Mona Lisa, Chartres Cathedral, all that kind of stuff. I don't know anything about that. But what I do know about is the geometric proportions of what the golden ratio is. And it's essentially the ratio between the top line on that rectangle and the sideline on the rectangle. And we'll talk about how that works and how that is. But it's a very simple ratio that can be used to design very complex things. It's like pi in the sense that it's irrational and it goes on forever, and it's sort of inherent in the way that geometry works. So what you do is you take a line and you make a square out of it, and then you bisect one side of it, and then you strike that line that you bisected it with up to the top, and then you make another square out of that, drag it all the way down, and that's your golden rectangle, right? So it's super simple. Like a child can do it. You can do it with a paper, with a compass. That was part of what I was trying to decide. What I was trying to get at with these is that it's super simple, and you don't actually have to have any math to do it. So the ratio is the ratio of the orange to the blue in this instance. And it's also the ratio of the orange to the blue, or vice versa in this instance. So it goes both ways, so to speak. And what starts to get interesting about that is that those two ratios are equal to one another, right? So the big blue is to the big orange as the little blue is to the little orange. And again, this all just happens as a natural part of the geography, or of the geometry. So then what starts to get interesting is that the ratio of the orange and the blue together, which is that new line there, is to the blue line the same way that the blue is to the orange line. So it's this kind of self-referential, it goes on forever, it never formally divides, and it's an irrational number, and it's been called the most irrational number. Again, like pi, it just kind of goes on forever. It's about 61.8, but it goes on forever, and you can use 6.1.8, you can use it in a lot of different ways. Okay, so that's the ratio, and so once you have that, you can do a whole bunch of other stuff. But that's the basic idea. It's not a number, it's a ratio. So what does it do? Well, you can do a bunch of stuff with it. You can build pentagons with it. So the blue and the orange on the right are the same proportion to each other as the blue and the orange on the left. So once you have those two, you can just fold it over and you've automatically got a pentagon without any kind of protractor. There's some other wacky stuff where the pentagons can then be used to construct golden rectangles, and it's this kind of self-similar structure that repeats all the way up and all the way down. Pentagons are cool. I spend a lot of time messing around with them. They're all self-referential. Once you get into the kind of basic Euclidean nature of some of this stuff, it can be really powerful. And if you want to nerd out about this stuff, I brought a compass and a ruler, and I will hang out with you. You can make them in lots of different ways. There's lots of videos on YouTube about how to construct pentagons. There's something very special about the relationship between 5 and 4. It gets deep. But so what can you do with it? So in this instance, what we're doing is the blue line, again, is this blue line, and the orange line is the other orange line, right? So what we're using is we're taking this line here, this is the long line, and then what we're doing is we're iterating, and then every time we iterate, we use the orange line, right? So the unit measure is the blue, and the iteration is the smaller one, right? So you move over one, you put down the orange, you strike a mark. Then you take the orange again and go on top of that mark, and you measure the distance between the distance that you've gone over from where the blue was. And you take that and you bring it down to the right. So essentially you're kind of doing this a lot, and you're kind of chopping off and rotating. And if you do this for long enough, and it doesn't take very long, you get these patterns. And these patterns, again, I'm not using any math with all of this. This is all done with the compass. It's just sort of inherent in the geometry. So you wind up with these kind of patterns. And then you wind up with these kind of patterns. And you can kind of link them all together. And they're irregularly regular, or regularly irregular. I'll talk more about that in a second. But you start to get these patterns that look like this, which is suspiciously what these look like. This is Hannah's Land of Learning, and where she talks about pi, and how it seems to be inherent in the shape of many, many plants, including pineapples. It's hard to look at this stuff for very long without running across V. Hart's amazing videos on math. Here she's using the Fibonacci sequence to generate pine cones, which are incredibly realistic. There's a relationship between the Fibonacci and the golden ratio, but we can talk about that over drinks. It's like that thing, like, how do you know there's a vegan at your party? They'll tell you. It's kind of like that with me and golden ratio these days. So we have this ratio, right? And it seems to be embedded in it comes out of fundamental geometrical relations, and it seems to be embedded in nature. And so according to Charlie, who's a great guy, and really, again, this has been in dialogue with him, he told me this: I use the golden ratio anytime I want to sample in a well-dispersed way when the number of samples isn't known ahead of time. And it's exactly analogous to why plants use it this way. So the sort of central thing that I'm trying to get across, or that I hope you'll get from this talk, is that it's a way of sampling and making things that is optimally efficient, even when you don't know how many resources you have, when you don't know how far you want to go. You can basically use it for as long as you need to, and then stop when it looks cool, which deeply appeals to my sense of aesthetics and parsimony. So Martin Roberts has a bunch of great examples about these sort of semi-irregular numbers. I encourage you to look at his work. There's a URL there. I'm going to post it a little bit later. But let's say you have a globe, and you want to sample points on the globe. You want to sample here, sample there, sample there, sample there. So you want to do three things, because you want to be as efficient as you can, and you want to cover as much ground as you possibly can. So you want to guarantee that each new point falls in the largest gap between previous points, right? So and I never want them to repeat. I don't want any grids, because I'm sampling, and I want to be able to add more points indefinitely, which is to say they'll never overlap one another. I don't ever want to do the same sample twice. So each new point falls in the largest gap. There's no regular patterns, and you can keep going forever, because the globe is big. So in order to show the efficacy of the golden ratio, I want to just go quickly forward to, or I want to talk about how it sort of sits in between two other kinds of sampling. So there's grid sampling, random sampling, and then golden ratio sampling, right? So the conceptual game I'll ask you to play is that you don't actually know what that image is, and that the samples are then going to kind of show different things about it. So this is a watercolor map that Stamen made, downtown Chicago, kind of regular, with some big geographic features on it. So what we're going to do is take a grid and lay it over this, and then we're going to move that grid around. Because again, remember, we don't know exactly where we want to start, how big it is. We don't know what's underneath it, and we're trying to get at what's under there. So hopefully this will be clear. And I've never shown these to anybody, so this is exciting for me. All right, so we have this image, and then we use a grid to sample it. And in this instance, we've had the bad luck that we've picked a grid size that's the same size as the street grid in downtown Chicago. So it looks like, not knowing anything about what's underneath it on the left-hand side there, that there's nothing there but streets and there are no buildings. And if I move it along, you start to see this also. So now, if you look on the left, there's no streets and only buildings, right? So it's not as efficient as it could be, and it's not as complete as it could be, and it introduces the potential for making mistakes about what's in your data set. The other one that you might try is random sampling, right? So no order at all, and you just strew a bunch of points across and use that. So there's big gaps, there's lots of clusters, and if we move this along, you'll notice that you're not really getting a really representative sprinkling of what's underneath. Whereas if we use golden ratio sampling, the results are quite different, and this is sort of the crux of things. So if I use golden ratio sampling, you can see there's no clustering. There's some kind of pattern, there's some kind of diagonal going on, but it's not regular, and you're not getting the kind of clumping and regularity that you get with grid or random sampling. So just some interesting things to note about this. This has the same kinds of lines as were seen in the other example that I showed. It's also got these and these. And I had such a fun time doing this because the more I did this, the more I found. And as I was talking with Charlie, he's like, no, they're not actually lines. They're slightly curved, ever so slightly curved. And so this is this kind of idea of a regularity. It's a method of guaranteeing the most regular irregularity from the beginning without knowing anything about the data set and not knowing anything about how it's been constructed. So we can do that. And what we're, again, guaranteeing is that we're doing the most with the least amount of efforts. I've got a few minutes left, and I know you're map nerds, so I'm going to show you just the difference between regular sampling of a viewshed, of a line around Mount Rainier. So if you all know what viewsheds is, because it's NACIS. So this is a viewshed calculated from points in a linear fashion around Mount Rainier. So it takes a while. Whoops. That's the good one, not the bad one. So this is the linear one. And you can see as I go around Mount Rainier, I'm kind of looking at more stuff. I can see more. But it's a very incomplete picture until about halfway through, and when you can start to see the full mountain. So that's at 184. Whereas if I use the golden ratio as a way of, is it clear what this is? This is like a line around Mount Rainier, and we're kind of sampling the viewsheds from it. So here, after about 7 or 8, I basically have the outline of the mountain already pulled out. And I can just kind of keep going. And what's happening is I'm essentially just filling in more of the detail, and it's kind of more and more little spots. So it's this kind of method for being able to kind of effectively sample. And then when you're done, you're like, well, you're done. And you can just pick off where you go. The other thing about it that's cool is that if 2 people are using the same method on a same data set, they're much more likely to get the same results instead of if they're using different grids and things like that. So it basically maximally expands your ability to do a sample. And also then to make maps on top of that. So a guaranteed method for doing the most with the least planning and almost no math is what we've got. And I love that because most of the time in my work at Stamen, I don't know how many resources I have. And I want a method that's going to be able to get me the best results possible without having to know in advance. So it's sort of a tool for exploring your way through an unknown data set and getting it to as good as it needs to be with the resources that you have. Charlie has put this code up on the web. It's kind of embarrassingly simple. It's got just a couple little numbers and 0.67, and suddenly you're off. So I'll tweet this URL out later. And if you're interested at all in this kind of stuff, I'm very interested in this, and so I'd love to chat with you about it. So thanks again for a warm welcome at NACIS.
We have time for one question before we move to our next speakers. All right, let's.
You said that the scale and the grid happened to coincide with that one map and the way the pattern was. Have you ever encountered anything with your golden ratio that revealed that there was a golden ratio scale?
That's such a great question and such a nerdy thing to say. Yes, unless your data set exactly matches the golden ratio, you're okay. But no, that's totally fair. Yeah, no, and what I've been encouraged by my team to say is not, this is a fail-safe method, only use this one, but it's more, I thought that for this crowd, when you've got different tools in your toolboxes, that this might be an interesting one to add to it. So that's the main reason. It's certainly not fail-safe, and it's not perfect, and none of that stuff, but it looks pretty cool, and that's important to me too. Okay.
Yep.
Thank you.
All right.